Hey, Didacture here. Another great math video for you. Today we are talking about limits, the indeterminate form, and L'Hopital's rule. Alright, so when do we use L'Hopital's rule and what is it and all that stuff? Well, let's go back and review a little bit about limits. Remember when we started in the beginning, we talked about limits and how we can find a limit of a function by a couple different ways. And some of the strategies that we talked about were, one, direct substitution. That's where I put the value of the limit where we're trying to find that x value, directly substitute that into the function, and I might be able to find the limit that way. Now, if that doesn't work, we can go down to the next item, and that would be maybe we have a polynomial in the numerator and a less degree polynomial in the denominator. So what we can do is we can factor things and we can see what cancels and so forth. And then once we cancel some things out, then we can substitute in for some direct substitution and maybe find the limit that way. Another thing we might be able to do is rationalize. We need to rationalize the denominator. We've got maybe a square root or some kind of issue in the denominator, so we rationalize the denominator and see if that will help. Then we can also multiply by the conjugate. Maybe we've got a root plus something, and so we might need that to create a difference of two squares. That's what the multiply by the conjugate does. It creates the difference of two squares. Oftentimes it'll alleviate the situation of a radical. So those are the normal top four ways. There are others, but what if those don't work? I mean, what happens if we can't execute any of those types of plans? Well, then we need something else. So we kind of look at the rules and say, well, if the limit as x goes to c, some x value that we're looking to see, what is the y value doing, of f of x over some g of x, gives us this form where, hey, if I direct substitute in, I get a 0, and I direct substitute in the denominator, I get a 0. So numerator and denominator both result in 0. They might also both result in something where it's infinite. So this could also be infinity over infinity, right? We could have that situation. So both of those situations where we get that, maybe we try direct substitution, doesn't work. We try factoring, we try rationalizing. Or maybe they're just not available given the function. So if these strategies are inconclusive, then what we can do is L'Hopital's rule. And L'Hopital's rule is very basic. It's take the derivative of the top, the numerator, take the derivative of the denominator, then substitute your c in, and that will give you the limit. Okay? Now I want to remind you, this is not the quotient rule. All right, this is not. There's not that much trouble to go into it. All we got to do, keep it simple. Derivative of the numerator, derivative of the denominator. It's not like I got to change this and move it up and make it a -1. Impact something like none of that happens. Okay, so let's look at some examples. Example number 1. We have the limit as x goes to 0 of 1 minus e to the x all over x. Well, if we try direct substitution, what we're going to get is 1 minus e to the 0, right, over 0. Well, anything to the 0 power is 1. So 1 minus 1 will be 0. And this is 0, obviously. So that gets ruled out. Now, I go to my strategies maybe, and I think, well, let's see. I tried direct substitution. That doesn't work. Can I factor it? Nah, it's not really something we can factor. I mean, 1 minus e to the x, right, over x, can't really factor that. Then I go, can I rationalize it? Well, there's not really a lot to rationalize in that denominator. Multiply by the conjugate, 1 plus e to the x? I don't know. I don't know that that's going to help either. So I'm going to go with L'Hopital. Let's try it. Let's give it a whirl. See what happens. So if I take the derivative of the numerator, well, the derivative of 1 is just 0. Then we have negative e to the x. Well, the derivative of e to the x is just e to the x. So we get negative e to the x. Okay? And then the derivative of x, well, that's just 1. So, and now when I substitute, not the limit is going to 1, but as of 0, right, of 0. So now if I substitute 0 in for my x, I get negative e to the 0, which is negative 1, and 1 just stays 1. So the limit then is equal to negative 1. All right, let's look at another example. Here we go. So here we have the limit as x goes to 3 of x squared minus 2x minus 3. Well, my first idea, let's try direct substitution. You find out through direct substitution that you're going to get an indeterminate form. So that won't work. So next we go is factor. Well, let's see if we can factor this thing. It looks factorable, and it looks like we'll get an x minus 3 here. So we do. We can factor this thing, and we get x plus 1 times x minus 3 all over x minus 3. And what do we notice? Oh, sweet. Those two factors can cancel, right? And now we're left with just x plus 1. And so now we can try direct substitution. The limit as x goes to 3 of 3 plus 1, the limit is 4. All right, well, maybe we didn't do that. Maybe we didn't factor it, or we didn't think of factoring it. Let's try L'Hopital's rule and see if that works as well. I mean, if the rule works, it should work, right? We just proved that in one case it's 4, and so we need to prove it again and see if it works again. So L'Hopital's rule says, hey, take the derivative of x squared minus 2x minus 3. Well, the derivative of x squared is 2x. The derivative of negative 2x is negative 2. And the derivative of x minus 3, well, it's just 1. So now I can go direct substitution. 2 times 3 minus 2 is 6 minus 2, which is 4. So yes, in both cases, we get the limit is 4. All right, one more. Here we go. This one, wow, you're looking at this going, wow, that's a crazy problem. This is the limit as x goes to infinity of x cubed in the numerator, and then e to the x over 2. Hope you can see that. That's x over 2 in the denominator. So we notice that as we go to infinity, this is going to be 0 and 0, because anytime we have... actually, this will continue to go to infinity. So we can either put that, or it'd be better actually if we change these all, because these are actually going to go to infinity, right? Over infinity. And then, so we get infinity over infinity. And then, well, that didn't work, so we're going to need to try the first derivative of each. So the derivative of x cubed is 3x squared. And then the derivative of e to the x over 2, or x to the 1/2, well, that's just e to the x over 2 again. And then I have to take the derivative of the upper portion. So that's the derivative of 1/2 x is just 1/2. So I get 1/2 e to the x over 2. Well, again, if this goes to infinity, that's going to go to infinity, and that will go to infinity. And now, so we go, well, let's do it again. L'Hopital, man, come on. If we can't get it here, let's do it one more time. Take the derivative of 3x squared. We get 6x. And then take the derivative of the denominator, 1/2. Well, again, it's going to be e to the x over 2. And then take the derivative of the u, or the x over 2, is 1/2. 1/2 times 1/2 is 1/4. Again, I plug in my infinite. 6x, that's going to keep going for infinity, right? That is also infinity. This one, the denominator, if I plug in x, this will also be infinite. So, man, we're stuck again. So we do it one last time. This time we take the derivative of 6x, and we get 6. And one more in the denominator, we get 1/4 times 1/2 again. That's the pattern. So we get e to the x over 2. Now when we go to infinity, e to the some power that's being fractionalized here, this denominator will grow without bound, right? So this denominator will grow without bound. And so as it grows, it will diminish the value of this 6, because if we take 6 and we divide it by 1, well, that's just 6. If I take 6 and divide it by 10, well, that's an even smaller number. If I divide it by 100 or 1,000,000 or 2,000,000,000 or something, we can see that that 6 just gets obliterated to 0. So, and that ends up being our limit of 0 for this. But notice, we kept working with L'Hopital's rule all the way through. So, anyway, hope you enjoyed that. That has been limits, indeterminate form, L'Hopital's rule. Hope you've enjoyed it. Have a great time. D-Daxter out. Thanks. Peace.